Alright guys, so we are going to be taking some time looking at what are called formal charges in this next installment. Alright, and so essentially what we want to be able to use formal charges for, okay, is to choose our most likely resonance structure. So this is essentially a lesson where we're just building off of what we did with resonance structures. So we spent a little time looking at when we use those first 5 steps for building our Lewis structures, those steps on that little help sheet I gave you, right? We use those first 5 steps. We go all the way through. We identify the valence electrons. We make sure our octets are satisfied. And we end up with more than one structure, right? Is one of those structures more likely than the others is essentially what we're trying to do. So when your Lewis structure steps give you multiple options, which would be those resonance structures we talked about, for where to place lone pairs and where to place bonds, is one option better than the others? And then how can you tell, of course? All right. And sometimes we do need to make that decision. Is one option more likely than the others? And so the next layer, and this would be step number 7 on that little help sheet, is basically how can we tell using something called formal charges. Okay? And essentially what we do is, once we know how to find formal charges, of course, which I'll teach you in this here lesson, right, we're always going to choose the structure with the fewest formal charges. Okay? So step number 7, it says, essentially, if you have multiple options and you want to figure out which one is the most likely, you're going to pick the one that has the fewest formal charges attached to it. Alright, so let's put this into context, see if we can make sense of this. So, when does it matter in terms of trying to choose which one's best? So I'm going to do a couple quick Lewis structures for you here with our carbonate ion and then with silicon dioxide, right? So carbon has 4 valence electrons, oxygen has 6 times 3, right? And then plus 2 more for that minus 2 charge. So 18 plus 4 plus 2 equals 24 valence electrons. Carbon's going to be my central atom. Going O there, O there, and O there, right? This one will end up, right? I'm just going to speed this along. I know, right? I'm going to need one of those double bonds because I've drawn carbonate before. Okay, again, I have to have that double bond there because that indicates my octet for the carbon. So that's my first 5 steps, right? I know I skipped a couple of steps in between by putting all the dots on there first, but I'm just in a little bit of a hurry trying to save you guys some time. All right. Now, of course, I could have put that double bond on one of those other oxygens. I could put it here. All right, and then go single bonds there, or I could put that double bond here. All right, and then put all my dots on there. And of course, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2. Whoops, sorry about that. So, those are my resonance structures for the carbonate. And again, this is a review. If that went way too fast for you, that means you need to backtrack and watch some of those previous lectures. Alright, so that's a review. That's why I did it so fast. But, those are my 3 resonance structures, right? That double bond that we see right there could essentially be on any one of those oxygens. Okay? Now, if we do a silicon dioxide, silicon has 4 valence electrons. Oxygen has 6, but there are 2 oxygens. That's going to be 12 plus 4, a total of 16 electrons, right? So I'm going to go with silicon, right, as my central atom. I'm going to go a line out to oxygen, another line out to oxygen. There's 2, 4, 6, 8. That is not looking good. And then 2, 4. Alright, oops. So, there we have all 16 valence electrons in there, but notice that silicon only has 2 lines attached to it, so only 4 valence electrons. I want to try to get my octet for silicon, right? So, here is where we're going to have to differentiate, right? I need to add 2 more lines to silicon to give it all of its 8 for its octet. All right. Now, I have options for how to do that. I can choose to go 2 double bonds. So I can erase those lines and go double bond there. And I can go double bond there. Or I can choose to go a triple bond on one side, single bond on the other. Or I could essentially go triple bond on the left side. Okay? So, in doing that, alright, the one thing I want you to notice is all 3 of these are essentially the same thing, right? It's just a double bond to an oxygen, and we're just having to try to pick which oxygen we want to put that double bond on. Okay? Now, on the previous ChemQuest, you guys learned that in reality, that double bond kind of circulates through, alright, in that resonance form, alright? Now, with our silicon dioxide, these two are essentially the same. This guy is different. Alright, and so what we're trying to do at this point now is use what's been determined experimentally with formal charges to decide which of these structures, alright, is better, right? A triple bond and a single bond, or 2 double bonds. Okay? So, formal charges here aren't going to really tell us anything, because it doesn't matter how we look at it, it's essentially the same structure. We're just putting the double bond on a different oxygen. But all of them are oxygens. Okay? Here, we do have a differentiation to make between these guys and this guy, right? This has 2 double bonds, this has a triple and a single. Alright, so formal charges would not help us here if we had to choose between those two. It would, however, help us differentiate or decide which of those structures, 2 double bonds or a triple single, is better for silicon dioxide. Okay, so that is when it does matter, when the 2 structures are not essentially the same thing. Alright, so how do we find a formal charge? So formal charge is a simple calculation between the number of valence electrons an element has minus the number of formal electrons shown in the Lewis structure. Whoops. I should say formal charge. Sorry about that. Alright, so valence electrons minus formal electrons gives you formal charge. Alright, so in the case of our carbonate ion, which we know has a -2 charge overall, alright, we want to be able to look at the Lewis structure and identify a number of valence electrons, okay, and then subtract from that the number of formal electrons for each element in the Lewis structure. Alright, and essentially the way we know how many formal electrons we have is each dot is 1 formal electron. Each line is also 1 formal electron. Now that's a slight differentiation from what we've been doing with our octet. Alright? And so what we have to understand is for the formal electron purpose, each line, remember, contains 1 electron from each element. And they share that, each share 1 electron to kind of give it what's sort of like a pair. Alright? But for the formal electron purpose, what we have to understand is that so for example, in this bond right here, okay, alright, so let's start with carbon here. So let's take this carbon element right there in the middle. So we know carbon has 4 valence electrons. I'm going to go 4 minus, right, and each line counts as 1 formal electron, and carbon has 4 lines around it, so that's going to be 4 minus 4 equals 0 for my carbon there. Okay? I'm hoping that's making sense to you. Right? So my carbon atom right here in the center, right, has 4 lines. Right? 1, 2, 3, and 4. Right? Each line counts as a single formal electron. So carbon has 4 valence electrons minus 4 formal electrons equals a formal charge of 0 on that carbon in the center. Alright, so I'm going to clean that up a little bit. I'm going to put a little 0 next to carbon. Alright, now going to our oxygens. The oxygen atom has 6 valence electrons. Alright, and so in this case I've got 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 6 valence electrons minus 8 formal electrons equals a negative 2. Oops, sorry. Minor mistake. Right? Those 2 electrons should not be there. Let's do that again. Alright? So I have 1, 2, 3, 4, 5, 6. I have 6 valence electrons from oxygen there. Minus 1, 2, 3, 4, 5, 6. Right? So this oxygen right there also has a formal charge of 0. They've got 6 valence electrons and 6 formal electrons. Now, these 2 singles, I'll just do these at the same time since they look exactly the same, right? They each have 6 valence electrons. So I'm going to go 6 minus, right? Now we got to count their formal electrons. I've got 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals negative 1, right? So this oxygen has a negative 1 formal charge. This oxygen has a negative 1 formal charge. Alright, so in this case, right, that is where that overall minus 2 charge comes from, right? It comes from these 2 oxygens right here and right there that have that overall minus 1. The 2 minus 1s add up to a total of minus 2. Okay? Now, what we have to understand there, so that's how we do our formal charge. Alright? And we're trying to choose the one with the fewest formal charges. Okay? So in the case of our carbonate options here, all options are the same. Minus 1, minus 1. Minus 1, minus 1. Minus 1, minus 1. It does not matter how we draw it based on those first 5 rules. All options are equally likely. Okay? Now, that may or may not be the case with my silicon dioxide. Okay? So, let's take a look. Let's differentiate between 2 double bonds and then a triple and a single. And keeping in mind that we end up with 2 triple singles, but they are essentially the same thing. So we're just going to differentiate between the triple single and the double double. Alright? So, let's look at this. We know silicon has 4 valence electrons. We know oxygen has 6. Alright? So, each line counts as 1. Each dot counts as 1. So for my silicon, right, I've got 1, 2, 3, 4 lines. 4 valence electrons. 4 minus 4 equals 0. Okay. For my oxygens, right, 6 valence electrons. 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. 6 minus 6 is 0. So structure A has 0 formal charges attached to it. There's none of the atoms have any sort of charge. Now, if I go to structure B, right, I'm going to notice that my silicon has 1, 2, 3, 4 lines around it, 4 valence electrons, so 4 minus 4 is 0. So the silicon still is 0. This oxygen, 1, 2, 3, 4, 5, 6, 7, I'm going to go 6 minus 7 equals negative 1. This oxygen has going to be 6 minus 1, 2, 3, 4, 5 plus 1. Alright, so back on the first slide. Okay, so which is better? Right, back on the first slide we said we're going to choose the structure that offers the fewest number of formal charges. Okay, so in this case we would then differentiate and say that structure A is in fact our best option because of the 2 different ways of drawing it. It has the fewest formal charges. Therefore, that's better. For carbonate, because they're all essentially the same thing, they're all equally likely. So, all equally likely. This one, more likely. Bam! Alright? So, formal charge, as we said, is valence electrons minus formal electrons gives us formal charge. Okay, you look at the formal charges in your different options. Once you've calculated all those different formal charges, you can then decide which option is best. Adios.